On this RAM, P0031 is the PCM flagging the O2 sensor 1/1 heater circuit as low. The truck may only show a MIL, but that heater helps bring the oxygen sensor online. So cold start fuel control and emissions behavior can be affected while the sensor warms up. Think of the fault areas in broad buckets: heater ground or heater control wiring, the O2 signal and return circuits, connector and terminal condition, the sensor itself, and only after the circuit checks are proven possible PCM control. Also remember that if the PCM detects a heater circuit fault, it can disable the internal heater driver for the rest of that ignition cycle, even if the fault comes and goes. Before testing the heater circuit, it helps to understand what the PCM expects to see from this oxygen sensor system. Normal range of the O2 sensor output is a 0 to 1, 0-volt analog to digital signal when the sensor is within the normal operating temperature range. If the sensor's reference chamber is contaminated, a negative offset output of up to -1, 0 volt may be introduced. Each O2 sensor return circuit has a 2-5-volt bias added, so the bias signal voltage should switch between 2, 5 and 3, 5 volts on a normally functioning sensor. If heater control is disabled, the affected O2 sensor bias signal voltage usually stays above 4-0 volts. A small amount of resistance, 3-4 ohms, may not set a heater control circuit code, but it can affect heater operation and set a sensor signal high fault. A heater circuit with 4-0-5-0 ohms resistance can increase the heater temperature reading on the scan tool for the affected sensor by as much as 700 degrees F compared to the other switching O2 sensors, and as little as 2.0 ohms can increase the temperature reading approximately 250 degrees F on the scan tool. On a normally operating switching O2 sensor heated to operating temperature, the typical duty cycle percentage will range between approximately 30 and 50%, and the typical heater temperature will range between approximately 1,200 degrees F and 1,400 degrees F on the scan tool. If the PCM disables the heater driver, the duty cycle will be 0%. Some signal and return faults can also skew the scan data. With the O2 sensor signal shorted to ground and the sensor cold, the bias signal voltage will show 0 volts, while the 0-1 raw voltage signal will read -2.5 volts and increase toward 0 volts as the sensor heats up. An open in a sensor return circuit will cause the bias signal voltage to read high near 5.0 volts and the 0-1 raw voltage reading to be near 2.5 volts for the affected sensor or sensors. With a short to voltage in the sensor return circuits, the affected O2 sensors will read 5.0 volts on the bias signal voltage, and the 0-1 raw voltage reading will be 0 volts because the signal circuit voltage and return circuit voltage are both 5.0 volts. On a cold engine start under that type of condition, the 0-1 raw voltage reading will start at 2.5 volts and decrease to 0 volts as the sensor warms up. Before getting into the circuit tests, make sure the basic checks are complete. Then check for any applicable service bulletins or flash updates for this fault. If one applies, handle that first and verify the repair before continuing. If none apply, use the scan tool to read DTCs in all ECUs, record what is there, save the scan report and related data, then erase the codes. Turn the ignition off for a minimum of 10.0 seconds, turn it back on, and reproduce the captured operating conditions. One monitor gate for this code is battery voltage between 10.4 and 15.75 volts, and the setting logic is the PCM detecting O2 sensor heater circuit resistance below approximately 2.0 ohms. If P0031 returns, continue into the circuit path. If it does not return, work it as an intermittent instead of guessing at a hard failure. The first hard circuit check is the O2 sensor heater ground side. Disconnect the O2 sensor harness connector so the circuit is isolated. Connect the positive lead of the load test tool to battery positive, and connect the negative lead to the ground circuit at the O2 sensor harness connector. Compare the bulb brightness to a direct battery connection. A bright bulb means the ground path can carry load, so move on. If the bulb is not illuminated and bright, repair the ground circuit for an open or high resistance, then verify the repair. For these load tests, use a tool that actually loads the circuit. A 3156 bulb has approximately 6.0 ohms of resistance when powered and draws approximately 2.0 amps of current. Many high-impedance test lights draw less than 0.1 amps, and that is not reliable for this kind of load test. The tool should draw more than approximately 0.75 amps. A 12-volt test light can be substituted if it meets the load requirement. If bulb brightness is questionable, voltage drop across the 3156 bulb can confirm what the circuit is really carrying. As an example, 2.0 ohms of resistance in the circuit being tested will cause the voltage measurement across the bulb to be 25% less than when compared to battery voltage, because the 2.0 ohms in the circuit makes up 25% of the total circuit resistance of 8.0 ohms. Keep components disconnected during load testing, and do not use this load test method on restraint system circuits. Next, check for circuits that are shorted where they should not be. With the ignition off, disconnect the O2 sensor harness connector and the PCM-C2 harness connector. Check continuity between ground and the O2 sensor 1/1 signal circuit, the O2 sensor 1/1 return circuit, and the O2 sensor 1/1 heater control circuit at the O2 sensor harness connector. There should be no continuity to ground on any of those circuits. If any circuit shows continuity, repair that circuit for a short to ground. Use the wiring layout and any inline connectors to isolate where the short is, then verify the repair. If there is no continuity to ground, install the Diagnostic 10436 adapter at the proper PCM harness connector. Do not probe the PCM harness connector terminals directly. That can damage the terminals and create poor pin fit. With the circuits isolated through the adapter, check the signal circuit, return circuit, and heater control circuit against all other circuits at the adapter. There should be no continuity between the circuit being tested and any other circuit. If there is continuity, repair the short between those circuits, then verify the repair. If the short checks pass, move into open and high resistance testing. Measure the resistance of the O2 sensor 1/1 signal circuit between the O2 sensor harness connector and the GPEC adapter. The resistance needs to be below 3.0 ohms. If it is not, repair the signal circuit for an open or high resistance, then verify the repair. If the signal circuit passes, measure the O2 sensor 1/1 return circuit the same way. That circuit also needs to be below 3.0 ohms. If it is not, repair the return circuit for an open or high resistance, then verify the repair. Now load test the O2 sensor heater control circuit. Connect the load tool positive lead to battery positive. Back probe the heater control circuit at the O2 sensor harness connector with the negative lead, and use a fuse jumper wire to connect that heater control circuit to battery negative or a known good ground at the GPEC adapter. If a PCM harness terminal has to be accessed, use the GPEC adapter. Compare the bulb brightness to a direct battery connection. If it is bright, continue. If it is not bright, repair the heater control circuit for an open or high resistance, then verify the repair. Keep in mind the GPEC diagnostic adapter can add up to 1.5 ohms of resistance to the circuit. Once the wiring can pass the load and resistance checks, reconnect the PCM-C2 harness connector and turn the ignition on. With the scan tool, command the O2 sensor 1/1 control to the maximum allowable percentage. Use a 12-volt test light connected to ground and probe the O2 sensor 1/1 heater control circuit at the O2 sensor harness connector. With the actuator commanded on, the test light should illuminate, and the brightness depends on the actuation percentage selected. Then command the actuator off and check the same circuit again. With the actuator off, the test light should not illuminate. If the light behaves correctly on command and off command, The path supports replacing the O2 sensor 1/1, followed by repair verification. If the driver response is not correct, continue to the connection inspection path before making a PCM decision. Before calling the PCM, inspect the related connections carefully. Perform any applicable service bulletins that have not already been handled. Disconnect all PCM harness connectors, any related inline connectors if equipped, and the related component connectors. Look for poor connector installation, damaged locks, corrosion, signs of water intrusion, damaged weather seals, bent terminals, overheating from a poor connection, terminals pushed back in the cavity, spread terminals, and poor terminal tension. Repair any condition found. Then reconnect the PCM connectors, inline connectors if equipped, and component connectors, making sure everything is fully seated and the locks are fully engaged. Erase the DTCs, operate the vehicle under the captured operating conditions, and read the codes again. If P0031 returns after that connection work, the path supports replacing and programming the PCM, then verifying the repair. If P0031 does not return, the wiring or poor connection problem has been repaired, and the repair still needs to be verified. Keep verification separate from testing. After any circuit repair, sensor decision, or PCM decision, erase the code, reproduce the operating conditions, and confirm the code stays gone. Takeaway: prove the wiring under load first, then prove PCM command control, and only make the sensor or PCM call after the circuit checks support it. For more diagnostic training, visit stepdiagnostics.com.